Perception should be impossible. So, according to early psychology, every image on your retina is compatible with infinitely many possible objects. And that means that you should constantly hallucinate the wrong world. You should constantly be wrong about what you're looking at, but you're not. So, either we're a miracle or psychology started with the wrong assumption, or maybe both are true. I actually like the idea that we're miracles, but we do need to explain it in a scientific way. And today we're going to see how Gibson tried to fix that by basically starting from scratch and asking, what is perception really all about? And one of the things that we're going to see today is that many things are possible or become possible when you use the right representation of the problem. And for Gibson, one of those key moves was realizing that we are organisms in an environment rather than passive observers in a idealized mathematical construct. So that idea that in our entire lives, we have always been an organism and we've always been in an environment, that was the beginning concepts that Gibson tied into perception. And then almost everything else flowed out from that, realizing that there is information in the environment that our perceptual system was created to move in. And that allowed us to come at perception in a completely different way. So, one interesting thing that this really brings into contrast, and this goes back to our trying to understand what is the human mind. So, this is a Mobius strip. And if you're familiar with a Mobius strip, it is a one-dimensional object. It only has one side. So if you follow the path of that tennis ball, you'll see that it never leaves the strip. It never jumps over anything. And yet it passes from what appears to be one side of the Mobius strip to the other side of the Mobius strip. And the reason is that it can do that is because it's really just a one-sided object. There's no top side, there's no bottom side. It's just one side. And perception might be like this if it requires both an organism and an environment. So, what exactly are we studying when we're studying the mind in perception? So, is the mind inside of our skull? Is it our brains? Or is it the relation between our brain and the world? Any thoughts on that? So let's push this a little bit more. If you remove the environment, so we have an organism, we have an environment. If you remove the environment, is perception still possible? hmm
I don't think so because then there's not really anything for you to perceive.
So you would say that it's impossible because there's nothing for you to perceive? Does anybody have a counter argument to that? That you would still be perceiving even if there was no environment? I stopped myself from saying the next word there because I think you're absolutely correct. When you boil it down to the definition of perception, it is the stimulation of it's the experiences that we have from the stimulation of our senses. And that stimulation has to come from the external world. So if you take away the external world, then perception is completely impossible. It's just theoretically, logically not possible. And then if you flip that, you have that idea that if you remove the organism, is perception still possible? And that too is an impossibility because this one tends to get a little bit more philosophical. But again, if perception is those internal experiences that we have, then there has to be a we in order to have those experiences. And if you remove the organism, there's no we. So it's sort of like that riddle about, or that, I forgot what they're called. I think Buddhists use them to meditate. It's the sound of one hand clapping. Is that a cone? It might be. If anybody knows, feel free to jump in. But the one about if a tree falls in the forest and no one is there to hear it, does it make a sound? And that argument brings into kind of contrast two different ideas. One is the stimulus there. So if a tree falls in the forest and nobody is there to hear it, does it distort the air that's in the forest and set up different compression waves? Absolutely. On the other hand, does that make a sound? Is it perceived as sound if nobody is there to hear it? Absolutely not. So again, we have that idea that if you remove the organism, perception is not possible. If you remove the environment, perception is not possible. So it could be that when we're talking about the mind, as at least when we're talking about it in perception, the organism and the environment are the mind. So much like the Mobius strip here, where they look like two different things, right? It looks like the Mobius strip has two sides. Maybe one side is the mind side and the other side is the environment side. It looks like, especially if you start to look at Gibson's work, that really there is no two sides to perception. It's not organism and it's not environment. It's the organism environment interaction, the two of them together, only one side. That's what is causing perception. That's how we understand perception, meaning that for perception, the environment is part of our mind. So it can be thought of as that cognitive system that we use in order to do cognition. So this discussion, when I was setting up this class for today, it kind of reminded me of this one really weird, wacky example from a comic book that I read called Doom Patrol. So this is the Doom Patrol run that was written by Grant Morrison. And Grant Morrison is a comic book writer that does get really weird and wacky sometimes. So this is his Brotherhood of Dada. The individual that is yelling, "It works," that is Mr. Nobody. He's the leader. And what he's talking about is that he found a painting that literally eats the surrounding world. And it goes, as you can see, recursively inside the painting. So the painting is in the painting because it ate itself. And then the painting is in the painting because it ate itself as well. And in the very next panel, his entire team is in the painting. And then they end up eating Paris. And then there's a whole bunch of shenanigans. But his origin story is really kind of a nice example of how we are never outside of an environment. We are always organisms in environments, because his origin story is when somebody took an organism, him, and put him into a non-environment, as much of a non-environment as you can have. So there's a description of the environment that it was completely white. It was painted in a way and it was curved in a way that there was no shadows. It was lit in a way where there was no change in any sort of pattern around you. It was just white everywhere you looked. And there was absolutely nothing there. And within about 3 days, it goes, by the end of the first day, I was completely insane in that first panel there. Those initial hours were very bad. I was assailed by doubts, by terrors, and by hallucinations of every conceivable configuration. The last panel, minutes became centuries became millennia, became eons. So he went bananas in that environment. And one of the things that's a really good kind of general concept to think about is that your mind was made to interact with this world. So first off, your mind was made to interact with this world, period. This is the world we were developed in. This is the world we were made to interact in. Your mind was made to interact with this particular world. If you take your mind out of the world, it makes your mind work in ways that it was not designed to do. And that feels like effort. So one of the things that I discovered when I was supervising a master's thesis on burnout was that the reason that nature is so calming, the reason that when people are, working really hard, oftentimes they'll say, you know what, I'm just going to go out to the park and take a walk. That's going to energize me. Or on the weekends, I'm going to go out into the forest and I'm going to spend some time in nature. The reason that nature is actually very calming to us, or one of the reasons, is because our visual system was made to perceive nature And you can mathematically analyze nature, analyze it into things like frequencies, into things like contrast, and the exact pattern of frequency and contrast that is in nature. And it is very different from man-made structures like this. So when we're in man-made structures like this room, our visual system is working overtime to try to process everything because our channels are not tuned to process what's in this room. But as soon as you go out into nature, into the forest, the channels that we have pre-tuned line up exactly with the information that we're getting from nature, and it just makes everything flow a lot easier. It gives you a calming sensation. Even though, if you know much about me, I'm not very pro nature because I kind of feel a little animosity towards a world that is almost always trying to kill us. So I remember learning that when you are lost in a forest, let's say that you are out camping, you are on a 3-day trip, and you get lost, in the forest, in the mountains. What do you think is the number one reason that people die when they're lost in a forest? Any ideas? Yep.
Dehydration?
Dehydration. So you will die if you don't get enough water. I think it's like 3 days you can make it before you die. Not the number one reason. Yep.
I want to say starvation.
Starvation, you can actually make it longer without food than you can without water. So also not the main reason people die. Any other speculation? Yep. Exposure. They die from exposure. And exposure is just being there, right? You're out in nature and you're exposed. So yeah, I don't want to make it seem like I'm super go back to the earth and fields. I have a healthy respect for nature because yeah, I know it's beautiful and it's trying to kill us. So all right, Helmholtz. Yeah, let's get it back on track here. So just a real brief recap so that we can launch into ecological psychology today. So Helmholtz made huge advancements in perception. He was a physicist, so he brought a physicist's toolkit to perception and said to himself, hey, you know what? Let's try to understand this human behavior, this human mobility, using the tools that I'm familiar with, which is physics. And his main contribution was to identify the fact that the pattern of light from any object that is coming on into your retina is compatible, is consistent, would be produced by an infinite number of different objects. So with his formulation of perception, the problem was, how does your perceptual system choose which of those infinite objects is the actual real object that's out there in the world? Is it the square that's really close to you? If it is, you better move out of the way very quickly. Is it the square that's really far away from you? If it is, you got some time before you have to move out of the way. So he came up with many different ideas. We went over last time the likelihood principle and why that's a non-starter, because for infinite numbers of possibilities, the idea of likelihood just doesn't exist. They all have a likelihood of 0%. So to choose amongst an infinite number of possibilities, you don't even have that ability. It should take you forever, and we know that it doesn't. So to try to solve this problem, Helmholtz came along and he said, well, let's do ecological psychology. And the starting point of this is to guide adaptive action. So the reason we have perception, the reason we have these sensations in our mind isn't so we can see a pretty flower or appreciate a beautiful sunrise. It's so that we can act in our environment. We can navigate it, we can find food, we can avoid danger. That is the reason why we have perception. So it's not mental inference from physically caused sensations, it's guiding adaptive action. And he mentioned or came up with the idea that perception is actually direct, non-inferential. We're going to look a lot about that today. And it's because it's from information gathered from the environment. So we have enough information in the environment that we don't have to infer. We don't have to have hypotheses about what's out there. We don't have to enable the likelihood principle. And perception is direct. It's picked up directly from the environment without any need for other forms of information to help us figure out what's out there. And this was a huge departure from what was the accepted framework, which came from physics. So in the accepted framework, we saw bodies in space. We perceived objects in space. They were abstract mathematical approach, and it was passive. The viewer had no agency in these physics approach because in physics, you have no agency in physics. You're just describing motion. So there's no need for humans to do things in physics. So they started with a approach where there was no need for humans to do things in perception. Gibson came along and said, well, let's change that up a little bit because this approach is not working. So let's try something different. So instead of bodies in space, instead of idealized mathematical functions in an idealized mathematical space, what we have is we have medium, substance, and surface. Medium is the things that we move through, such as air. There's always air around us, or water. Water is another medium. Substances are the things in our environment that have width and depth and height. And then surfaces are where the substances meet the medium. So where the table meets the air, that is the surface of the table. And what we perceive are not objects in space, but what we perceive are surfaces in a medium. So it's a subtle shift, but as we're going to see, surfaces come with a lot of information. And this is not an abstract mathematical approach, but rather it's an approach that says, hey, you're an organism and you're living in an environment, and that environment is not abstract. That environment is very detailed. It's occasionally very messy, but it is essential in order for perception to occur. And because we're an organism in an environment, a big move for his ecological psychology framework was that we are active. And we're going to see that much of what he talks about can only be noticed if you have an organism that is moving. So much of what we count on in order to perceive the world comes from information that we get when we're actually moving. So we have to have an active observer. And then we talked last time, we introduced one of his big ideas that since we're dealing with substances and surfaces, and we perceive surfaces in a medium, and we're an organism in an environment, we should take a look at what information do the surfaces in our environment actually have. And one of those big pieces of information is texture. So things in our environment, they have these repeating units that make up their surfaces. And those repeating units are texture. And those repeating units might be randomly sized. But the key thing here is that on average, the average size of these units in any one area of texture is the same as the average size of the units in any other area of texture. So you might find one unit that's a little bit bigger and one unit that's a little bit smaller, but in any area, the average size of these units is just about the same. We have it on trees, we have it on tiles, not tiles, towels, then we have it on tiles. So even man-made things will have texture and repeating patterns. You have it in grains of wood, you have it in knitted tablecloths, you have it in fur on animals, you have it in rocks in a riverbed. So all of those rocks are differently sized. But importantly, repeatedly, the average size of rocks in any one area is the same as the average size of the rocks in any other area. And those repeated units of texture give us information about the world that we are in. And then the last thing that we kind of give an example of is this field of sunflowers. Again, we have repeated units of the world giving us this texture. And importantly, this structures the information that is coming to your eyes. This structures the information that your perceptual system can access. And that information, as we're going to see, comes in the form of the differently structured light. And when you're talking about a real world with real things in it, then you can easily see that in that area, there's a certain pattern of light that is coming to your eyes. And in this area here, there's a completely different pattern of light that is coming towards your eyes. However, the more you idealize this real world environment, the more you simplify it so that you can apply mathematical formulas to it, like they do in physics. If you strip away enough information, it makes perception impossible. So when the texture is gone, we don't know what we're looking at. This is an unsolvable problem. This is a solvable problem. This is Gibson's approach. This was physics' approach. So texture was one of the first big things that Gibson introduced in the idea of this might be where the information is coming from. All right, so that was just a really brief recap of the backstory of psychology, ecological psychology, and the idea of texture. Now we're going to move to a very important idea, which is the ambient optic array. And we're going to see that it has two types of structure, perspective structure and invariant structure. And then hopefully we'll have time for this. We're going to take a look at affordances because it is one of my favorite topics in ecological psychology. Not because I understand it super well. It is a very complex topic, but the way they talk about it, I think, is just one of the greatest things I've ever heard. So hopefully we'll get there today. If not, we will cover affordances. They are too awesome not to. All right, ambient optic array. So ambient optic array is one of those terms where you pretty much know what each term means, but when you put it together, it makes something super complex. So the ambient optic array is exactly what it says on the tin. It's ambient, it's an array, and it's optic. It's for visual perception. So what we mean by array in this term here is to have an arrangement. So this ambient optic array is optic, is visual, and it has some sort of an arrangement. And the ambient part is ambient at a point, and what that means is that this array, this arrangement of light, surrounds a position in the environment that an observer could occupy. So it's ambient because at any point in this environment, there is an optic array just waiting for your eyeball to encounter that point in this environment. So there's an optic array where I'm standing. There's an optic array by the door. If you got on a ladder and stood in front of the screen, there's an optic array over there. There's an optic array exactly where you're sitting. And it's ambient because it's there at every single point. So if you ever are walking down the hallway and for just a millisecond, everything goes black and then it all comes back, well, you have just encountered a point in your environment where there is no optic array. Either that or you're having some sort of medical issue. But if you're not having a medical issue, you have just encountered a point where there was no optic array, there was no information, and the world looked black. That doesn't happen. So this is always something that is available in the environment. And the reason it's available, and again, this is the reason why mediums are so important in ecological psychology, is because light is ambient. So let's take a look at that really important concept, especially the light being ambient. So this is going to take a diagram from the Ecological Approach to Visual Perception, written by James J. Gibson. This is Gibson 1979. Remember I said that you need to cite what year Gibson is because he changed his mind as he was proven wrong during his scientific career. So we're going to take a look at this diagram over here. So let's just zoom in a little bit. And then I'm going to do that Star Trek thing where you like enhance. There we go. And let's get rid of the textbook. Let's move it into the center a little bit. So this is a diagram explaining why we have ambient optic arrays in our environment. So let's start off with step number one. And step number one is directional radiation from the sun. So we have light coming from the sun. And because the light comes from so far away, it's basically straight lines when it hits the earth, right? So we see all those lines coming in. Those are the straight lines that are coming from the sun, the straight lines, which is the way that light travels through any particular medium, is coming there in straight lines. However, it is going through a medium. It's not going through the vacuum of space. And what that means is that it interacts with the particles that are in this medium. And what those particles do is they start scattering the sun's rays. So the sun's rays get scattered by particles in the atmosphere, and those scattered light rays then travel to surfaces like the surface of the earth, and then they get reflected away from the surfaces, and they continue to move and they continue to scatter. And through this scattering and reflecting and re-reflecting and rescattering and more reflecting, what happens is that you get diffuse illumination in the medium. And that is why your optic array is ambient. So that is why at every single point, even though the light is coming from the sun, even though the light in this room is mostly coming from that projector, we have light everywhere because it bounces off the air, it bounces off the screen, it bounces off the surfaces, it bounces off of you. And then we have this scattering of light coming in at every direction. All right, so let me ask you this just to see if we can drive this home. So let's say that this wasn't true. Let's say that light only traveled in straight lines and it never scattered. What do you think this world would look like? Mm-hmm.
We wouldn't have shadows.
We wouldn't have shadows. You're close. You're close. So we would still have, so shadows are where you have obstruction of the light in a certain direction. So you would still have shadows, but what might those shadows look like? Do you have an, yeah? They would be pitch black. So any of those kind of like soft shadows that you see in our world, any sort of things that kind of fall at a gradation, you wouldn't have that. You would either have light is there or light is not there. So you would have shadows, but they would be absolutely sharp, line, razor edge line sharp. So if you had shadows that were absolutely sharp, what would faces look like in that world? Let me just kind of push this a little bit more. Have you? Yep.
You'd be able to see every wrinkle and every detail on a person's face unless you have a light pointed at every single point in their face.
So you would be able to see every single detail, every single kind of wrinkle and things in their face, unless you had light pointed directly at their face. So that is one of the things that would happen. Any sort of shadows on a person's face would be magnified, right? So that's part of the reasons why the wrinkles would show up, because if your wrinkle was just a little small wrinkle, but it cast a shadow, that shadow would be black and it would be harsh. And you can kind of imagine, have you ever seen somebody and they have a bad photograph and you're like, "Oh my gosh, this photograph of you looks terrifying. What happened?" And they're like, "Oh, it was harsh lighting." Right? It was really harsh lighting. What they're saying is that the lighting was mostly directional, right? There was very little scatter. And there's a reason why, if you ever see photographers taking photo shoots, they will have those diffusers everywhere to bounce light back onto people, if they need to. And there's that time of the day, it's called golden hour, when everybody wants to shoot film and everybody wants to take photos. And I think it's like just about now, I think at like 4 or 5 o'clock, I think is the absolute golden hour time, because that's probably when the light is the most diffuse. So yeah, I mean, this is why our world looks the way that it does. And if it didn't, and we had drawn the Mona Lisa under under only directional light and not diffuse light, well, let's take away the color just a bit so we can make this a little bit easier to see. On the left there, that's what she would look like under ambient light. And if we take a look at what she would look like under directional radiation with no scattering, no bouncing off of her, that's basically what the painting would look like. So you can take a look at The fact that those shadows would be massively sharp. You take a look at her jawline over there. There's a lot of soft shadows. There's a lot of transition from, light gray to dark gray. In the directional radiation, you don't have transition, because transition is the light that is falling on her face and she's obscuring some of it, but then some of it bounces off her shoulder, or some of it bounces off her dress, or bounces off her hands, or is bouncing off the walls and starts to light the under part of her chin. If it's just directional and it doesn't scatter after bouncing off your clothes, then she would have very harsh shadows and would just not look, would actually, kind of look a little terrifying, to be honest. Harsh lighting, poor harsh lighting for Mona Lisa's portrait. All right, so that's the ambient optic array. So it's possible, again, because we live in the world that we live in, because we're in the environment that we're in, it has air, it scatters light, it gives us that ambient optic array. So every position in the environment is surrounded by this ambient optic array. And what that means is that any position an observer is in is automatically surrounded by an ambient optic array. So anytime you're in the environment, you're going to encounter an ambient optic array anywhere that your eye is. And that's why the environment just doesn't disappear and then reappear, and then disappear and reappear. It doesn't go pitch black, back to the environment, pitch black, back to the environment, because this ambient optic array, it's ambient, it's everywhere in our environment. All right, so that's the ambient part of it. What about the array part of it? What does it mean to have an arrangement? So to have that arrangement, it means that the light, this ambient light, is actually structured by the environment. So what do we mean by structured by the environment? Well, an easy way to think about it is to think about one of the few environments that you could possibly find yourself in where there is no structure in your environment. So remember I told you we usually don't have or encounter environments where we don't have at least some environment that is structuring the light. There is one exception other than Mr. Nobody in his transformation chamber, and that is very, very heavy fog. So if you have ever been in super heavy fog, and I mean the kind of fog where you're trying to walk around and you're like, I can't see the hand in front of my face. I can't see more than like a foot, 2 feet in front of me. If you're ever in super heavy fog, then you are in an environment that has an ambient array. So there's still light, diffusing around in the fog, but it's not structured. So it's not an ambient array. Sorry, it's ambient, but it's not an array. It's not structured. And when you start to lift the fog, basically what you're doing is you're starting to add structure. And what structure means is that different parts of your environment look different. And the reason they look different is because objects in your environment are structuring the light that is reflected towards your eye in that ambient optic array. The objects in your environment determine the shape of that ambient optic array. They structure the shape of that ambient optic array. They're what give it structure. So you know that you have a structured array when you take a look at different parts of your environment. And if one part of your environment has a different light pattern than another part of your environment, then you are in an ambient optic array. And that array is the structured light that is being reflected by those objects. If I put you in fog, then you have no structure. You have no array, because area A looks exactly like area B. But as soon as you have an environment, area A looks different than area B, because the light now is being structured in different ways. All right, so let's take a look at this in diagram form. So here we have an environment. We got a tree, we got a gazebo, we have ground and blue floor, I guess. We have a bird flying away. And you can see that little pie diagram, that little pie chart in the middle there. The center of that pie chart, that is a position in the environment. So that's a position in the environment that an observer might find themselves in. And the shape of that pie with all its different slices, that is the optic array. That is the structure of the light at that point. So you'll notice that a large part of the bottom of that pie is blue because the floor is structuring the light that is entering that point in the environment. A large part of the structure of that array is green because the leaves on the trees are structuring the light that end up being that slice of the pie. And on the right side, a large slice of that pie is yellow because that gazebo is structuring the light and determining that that much of that ambient optic array is going to be consumed, or is going to be not consumed, is going to be dedicated to the gazebo. And then what happens is that that structure changes as you move through your environment. So if you were able to jump really, really high and you jumped up to that position there, that pie looks much different than the pie below it. So there's way more of a white slice now that you're up near the sky, way less of a blue slice now that you're further away from the ground. The green slice has moved from the approximately 10 o'clock position now down to 8 o'clock position. So the environment structures the light at different points in the environment, and that is your ambient optic array. So let's take another look at this just to kind of really solidify this somewhat slippery concept until you really kind of get it down. So let's say that we have this environment, so a massive tiled field. And in this environment, we have ourselves a tree, and we have a girl walking her dog. And that girl is going to have a pretty bad day today because Samara from the Ring series is actually there. And she's also being chased by a T-Rex. That might be a little bit too much. So let's get rid of the T-Rex. So let's say that that's the environment that we find ourselves in. Every single one of those objects is reflecting light. Every single one of those objects is structuring that light that is getting reflected in multiple different directions. Okay, so that's, again, it's very important. It's directional light. It travels in straight lines, but it's being reflected in multiple different positions and directions. And if we take a single point, like that little circle right at the bottom left of the roots of that tree, right? So, that point right there. If we take that point is sending light to this particular viewpoint right here. So we can draw a line of light from the roots of that tree to that particular viewpoint. And then we can continue to do this with other parts of the tree. So we have a leaf that is sending, we have another piece of root that's sending a line to the line of light to the viewpoint. We have a leaf that's sending a line of light. We have another leaf that's sending a line of light. We have another leaf that's sending a line of light. Tons of leaves that are sending these lines of light. And what that basically does is you can think of this visual cone, this cone of light coming in there, as a tree-shaped bottom of a pyramid. So it's like a pyramid where the bottom of the pyramid is tree-shaped. And that is the tree structuring the light that reaches your visual system. And the girl walking the dog has the exact same concepts. So the dog and the girl have different points that are reflecting light towards that particular viewpoint. And then Samara from the Ring, she also has points that are reflecting light towards that particular viewpoint. And that is your ambient optic array, structured light from objects in the environment. And if somebody was to occupy that position, they would be able to perceive the environment, perceive the tree, perceive the girl, perceive Samara from the Ring, because that ambient optic array is giving them that structured information. All right. So any questions on the ambient optic array before we move deeper into the ambient optic array and uncover its two types of structure? All right, two types of structure. So your ambient optic array, it looks like it's just one thing, but it's actually made up of two types of structure. And those two types of structure are perspective structure and invariant structure. And perspective structure is the structure that's mathematical that we completely understand. We know everything there is to know about perspective structure. And invariant structure is one of the main goals of an ecological psychologist is to discover these invariant structures. So perspective structure, very straightforward. Invariant structure, a little bit trickier. So let's start with the straightforward one, which is perspective structure. And perspective structure is the structure that determines, or the mathematics that determines the structure of the ambient optic array. It is what determines the structure of the light entering your eye. So it is the projective geometry, which we don't need to know how to do, but we just need to appreciate that that is what this is coming from. It is the perspective geometry that for any position in the environment determines how big those slices of pie should be and where should those slices of pie be. So it's just projection, it's just a mathematical formula, and that is what determines the size of the slices and the position of the slices. The perspective geometry is what determines the shape of all of these pyramids that can be occupied at a particular viewpoint. But the question then becomes, and this is one of the questions that was very difficult to solve before Gibson's ecological psychology. One of the big questions in perceptual research and in perception psychology is that, all right, that's fine and good. We have this perspective structure. It's making these cones, that we can pick up the information from. We can be in that position to see those cones. But then notice those cones change as soon as you move. And yet we don't perceive a changing world, right? So the cones over here are different than the cones over here. And as this person continues to walk, notice that those cones continue to change. They change their shape, they change their angle, they change how tall they are, they change, just about everything about them. And yet you would not perceive that tree is getting bigger as you move closer to it, or Samara is getting smaller as you move farther away from her. And this is just the way that our visual system works. We perceive constancy in a world that is unchanging, and yet the perspective structure that comes to our viewpoint is constantly changing as we move through this world. So your perspective structure, that changes with every change in your position. But your world, and importantly, your perception of your world, does not change. So this led Gibson to speculate and hypothesize and theorize that, well, maybe there's another structure that is underlying this perspective structure, and this is invariant structure. And the invariant structure does not change when the point of observation changes. So there's a structure in that pattern of light that does not change as you move through your environment. And this unchanging invariant structure underlies that perspective structure. So it's almost like two hands on top of each other. You have the perspective structure, and then you have the invariant structure, and the invariant structure underlies that perspective structure. All right, so invariant structure may sound a little mystical and magical until you actually discover one. So let's take a look at some examples of these invariant structures that exist in our environment. And the first one that we're going to talk about are the units of texture on the ground that an object's base covers. So if you ever wonder why do things not look like they're getting bigger or smaller as you move towards them or away from them, one of the reasons is because the units of texture on the ground that an object's base covers does not change. It is invariant. So let's take a look at a schematic version of this. So here we have tiles. When you're learning ecological psychology, tiles are great because they're very clear. They're very easy to count. So don't get hung up on the fact that it's an artificial man-made type of environment. It's just great for explaining these things, and then we can get a little bit more into real natural environments. But the units of texture that an object covers does not change regardless of where you are in that environment. So here we have a can, a blue can, and notice that its base from one end to the other covers one entire tile, right? So its entire base just covers the width of a single tile. And it doesn't matter if this can is close to you in your environment, or if it's far away from you in the environment, or it's some middle distance between you in this environment, it will always cover one tile wide. Its base will always cover that one tile. And if you were in this environment and you started walking towards this tile, or the tile started walking towards you, notice that as it gets closer and closer, it only ever covers one tile. At no point does that change. So the perspective structure of this can changes all the time. However, the relation between the base of that can and the ground that it's on does not. And that can always covers exactly one unit of tile, one unit of texture on this ground. And it doesn't matter where it moves or how close it is to you, it will always cover that one unit of texture. And it works in schematic versions of the ground plane like this, but it also works in non-schematic versions, so more real-world scenarios. So if you were to count the number of rocks, which is what your visual system is doing, that this can covers as you move through the environment, it does not appear to be shrinking because it seems to cover the same number of rocks regardless of how far away that it is. And that is one of the reasons why it is so important to deal with the actual environment, because a real environment has rocks in it. A idealized physics plane does not have rocks. So this kind of relation between the base of your object and the environment is only possible if you're dealing with a real environment. And the other thing that is something that kind of made me I was learning about Gibson years old when I learned about this. In this environment that we actually live in, just about everything that we see and everything that we encounter is either on the ground or it's attached to something that is on the ground. So take a look at this room that we have here. You are either in direct contact with the floor, or you're sitting on a chair that's in direct contact to the floor, or something is attached to the wall and it's in contact with the wall, and the wall is in contact with the floor. Just about everything in your environment is in contact with the ground or in contact with something that's in contact with the ground. Yep.
What about a plane?
What about a plane? Yes.
Airplane?
Yes. Not in contact with the ground. So what would you predict would be, would perceiving plane size, plane distance be easier or more difficult? Yeah, it is more difficult. And one of the reasons that it's more difficult is because they're not on the ground. So one of the kind of classic examples of that is, has anybody ever seen like a flock of birds? And you're like, oh, there's a flock of birds and they seem to be a certain distance away. And then they fly in front of a tree and you're like, oh my gosh, they're way closer than I thought. Or they fly behind a tree and you're like, oh wow, they're further away than I thought. Like it's difficult to judge how far away birds are. It's because you have no ground. You have no ground in when you're looking at them in the sky. So it's really hard to use this information when that information is not present. So the other place that this happens is in if you're in the water. So if you're diving, you're doing some deep sea diving, and you're looking through the water and you see something far away, and you're like, has anybody here seen Finding Nemo? Do you remember that scene where they're looking for directions, and Marlin and Dory, they're like, oh, let's ask that fish, and they get closer and closer, and they're like, wait a second, that's not a fish, and it ends up being a whale. That's because that's actually a really insightful psychological observation from that movie is because there was no ground. So as they moved closer, the thing looked like it got bigger, and eventually they were able to perceive it as a whale. Again, it's exactly that kind of idea where if you take away that information, then perception becomes very difficult. So the amount of times you'd be wrong about how far a bird is when it's flying is way more than the amount of times you would be wrong about how far a bird is when it lands on the ground. And yeah, as if I can make these slides up on the fly, this orientation looks like 3 cans of the same size. But focus in on that red can over there. It looks like it's the same can, it's the same size as the 2 blue cans as it moves around. But if I add one more piece of information, which is its shadow, indicating that it is now flying in the air, then all of a sudden it does not look the same size as those other cans. It looks much smaller as it moves through this environment. So contact with the ground is the default. Not contact with the ground leads to weird things being perceived. And again, it's because of the environment that we lived in. And it would be really interesting. And I know scientists who have done this mostly for color vision, but it would be really interesting to study fish and study fish vision, because if you're able to navigate in a world, that means you're picking up the invariants. So it could be that an invariant that fish pick up is how clear does the object look. And if an object is really fuzzy because its light is trying to travel through tons of water, then they perceive it as being far away. But if it's really clear because the light doesn't have to travel through too much water, then you'll perceive it as being closer. So texture would get replaced by the fuzziness of the light. And that literally is one of the big jobs in ecological psychology. It's figuring out what are these invariants that make perception possible. All right, and then this idea of having the perspective and invariant structure and having the invariant structure underlie the perspective structure. This is one of the reasons why action is so important in perception. And you can imagine if I had one hand on top of another hand like this, the easiest way to see that I actually have my 2 hands here would be for me just to start moving my hands. Because when they're lying on top of each other, the back hand is kind of hidden. But as soon as there's motion, all of a sudden you can say, oh yeah, I can see what's the invariant structure and what's the perspective structure. So this active perception can sometimes help us separate this perspective structure from invariant structure. So a kind of schematic example of this, let's say that we have these 2 objects here and we have this line, and we are wondering, what is the invariant rule about how these objects travel? So in a moment, I'm going to show you how these objects move. But if we're trying to figure out what is that invariant rule about how they move, well, when they're not moving, we can't tell. There's no information. But as soon as they move, we can sense that invariant structure and we can say, oh, okay, the rule for these 2 objects is that regardless of how they move, they stay equally distant from each other. That does not change regardless of where they move. So that is the invariant structure for those 2 objects revealed by the motion. On the other hand, you could have 2 other objects and they have a different rule. Again, no idea what that rule is until things are set into motion. And now you can see that the rule is that the 2 objects do not stay equidistant from each other, but regardless of where they are, they stay equally distant from the line. And that is only visible or viewable when you are in motion. So this is one of the reasons why, if you're ever trying to see something, has anybody here ever kind of like struggled to see something, or maybe you're looking for a person in a crowd, or you see something in the distance and you can't quite make it out? What are some strategies that you might use? What are some things that you might do? Mm-hmm. Okay, so you would cover your eyes with your hands, and what might that do?
lights that are distracting me.
So you might have too much structured light coming into your ambient optic array. So you're trying to reduce that, or at the very least, trying to reduce some of the direct radiation. Like you said, it's too much lights coming into your eyes. That's kind of direct radiation, not reflecting off of anything. That's actually super interesting. I never thought of it that way, that when you're putting your hands over your eyes to see like that, what you're basically doing is you're blocking out directional radiation that is not reflecting from objects. And that directional radiation is not going to help you find objects unless it's reflecting off of objects. So yeah, that's actually a really, really interesting insight. And that does help you kind of see the object that you're looking for. Any other strategies people might use yet?
Walk closer to the objects by hand.
You walk closer to the object if you can. Or in general, what might you do? Walking closer is a variation of we're close. It's a very, I mean, you're right about the walking closer. And what that does is it does bring you closer to the object that you're looking at. But what it also does is it also puts you in motion. And if you've ever sort of had a struggle to try to see something, and let's say that you couldn't move closer, oftentimes what people do is they start doing this, and they start going, what's going on here? And what they're doing is they're trying to separate invariant structure from their perspective structure. Because here, when they're staying still, mostly perspective structure, you can't see the invariant structure, or you can't reveal the invariant structure. But as soon as you start doing this, all of a sudden the invariant structure just kind of pops out. All right, I'm going to share. I think this will be my final aside. Me doing this, I kind of had a flashback to another class that I was teaching. So it's my experimental psychology class, the methodological course. And I just wanted to show that what a variable was, right? So we were it was very basic. It was like week 2, and we were just defining variables, and variables are characteristics that can take different values. So I wanted to use the example of height. Height are different. People take different values on heights. So I found this picture where somebody had put the heights of all these famous actors and listed, put them all in a row and then listed their heights. And this one student in my class, they must have had a parasocial relationship with Michael B. Jordan, because when 5'10" popped out above his, his image, they started doing this, like moving would make it 6 feet tall, right? It was like anything, to kind of keep the fantasy alive. So yeah, we learned a lot that day. But yeah, so you move around, and that again reveals that invariant structure, the invariant 5-foot structure of Michael B. Jordan, I guess, but it reveals it when you move. All right, so observer position is another invariant. Okay, I got sidetracked. Where you are in the world, the space you're occupying actually has invariants that indicate where you are. So the ambient optic array actually specifies where you are in the world. Now, you might think that that's something that you would just know, but again, just because it feels simple or trivial in our minds does not mean that it's not massively complicated to do in our perceptual system. So what is an invariant that can specify where you are in the world? So we're going to play a little game right now. And this little game has to be, it deals with an environment. So we got the ground, we have a nice sunset probably, and we have a road. And the game that we're going to play is simply called On the Road. Did that backwards. On the road or off the road. So I'm going to show you some images. And what I want you to do is I want you to determine, are you on the road or are you off the road? All right. So that's all. So from your point of view, are you on the road or are you off the road? Here's scenario number 1. So hands up if you think that you are on the road. Hands up if you think you're off the road. Okay, so most people think in this case that they're off the road. So I mean like off to the side of the road. You're not going to get run over by a car. Let's put this in adaptive action. If you're in this position and an oncoming car stays on the road, you're not going to get run over. All right. Scenario number 2. How many think that now you're on the road? All right. Anybody think you're off the road? All right. Most of the votes for on the road. Last one. How many think you're on the road? How many think you're off the road? Okay. I actually lied. That wasn't the last one. Is the last one. How many think you're on the road? How many think you're off the road? This one's a little bit closer. So let's go back to this one. So how did you determine that? Did anyone here kind of calculate angles in their head? Did anybody think to themselves, well, the tangent of that particular angle there would indicate that, or did anybody measure pixel distance or anything like that? Okay, so what do you think was constant? What do you think? Let's see, let's do some ecological psychology work here. This one is off the road. This one is on the road. This one is off the road. So what is different about this versus this? Anybody want to speculate? Yep.
One thing that I looked at was whether or not the center of the screen was in between the lines.
So on the road is when the center of the screen is in between the lines. And then off the road is when the center of the screen is not in between the lines.
Like the bottom center.
The bottom center. Yep. That's it. That's the invariant relation. Very simple. Tells you whether you're on the road or you're off the road. So what we have is that if you have a road going off into the distance, because of the way that the light is structured, you have a vanishing point. And the invariant relation is that if road edge number 1 is on one side of the vanishing point and road edge number 2 is on the other side of the vanishing point, you are on the road. So this is on the road. So there's the left side and there's the right side. This is on the road because road edge on the left is, road edge 1 is to the left of the vanishing point. Road edge 2 is to the right of the vanishing point. This one is off the road because road edge number 1 is to the right of the vanishing point. Road edge number 2 is to the right of the vanishing point. So that is invariant. That is the invariant relation that tells you you are off the road. So you don't got to figure anything out. One road edge to the right, second road edge to the right equals off the road. And again, for the one that was on the road, we got road edge 1 to the left of the vanishing point, road edge 2 to the right of the vanishing point. And for the last one, we have road edge 1 to the left and road edge 2 to the left. So if they're, just to kind of throw another invariant in there, if both road edges are to the left, not only are you off the road, but you're on the right side of the road. If both road edges are to the right, not only are you off the road, but you're on the left side of the road. So if you want to try this in your actual environment, make sure there's no cars coming either way. But if you were to look down your road and start on one, okay, don't do this. I'm just going to tell you what's going to happen. If you were to stare down a road and start on one side of the sidewalk, you would notice that the two sides of the road are to the left of the vanishing point. And then if you were to sidle all the way across the road to the other side of the sidewalk, you will see those edges go on either side of the vanishing point and then move to one of the other sides. So please don't do that, because I want you guys back in class next time. I don't want that on my conscience, but it would happen. This reminds me of another Gibson story. So one of the great things about being supervised by somebody that was supervised by Gibson is that you get a lot of the stuff that didn't go into the textbooks. So when you are driving in a car, there is this optical pattern that that lets you know that you're staying on the road, right? There's an optical pattern that flows as you're traveling through your environment. And if you're on a straight road, the optical pattern when you're looking forward is just a reverse of the optical pattern when you're looking backwards. What that means is that if you are on a straight road, you are just as able to navigate that road if you were looking forward as you would be if you were looking backward. So you could safely on a straight road drive like this, going forward, right? Not in reverse, but going forward. You could drive like this and you could stay on the road. And Gibson's wife did not believe that. And he tried to prove it to her. And I think the experiment lasted about 2 seconds before she freaked out and made him look back forward. But yeah, it's invariant, right? One side of the road, you can do that looking backwards as long as you're on a straight road. There's a lot of keep looking forward. Okay. So this idea of invariance, they provide the information for perception. It's not clues, it's not heuristics, it's not guesses, it's specification. It's 2 lines to the left, 2 edges to the left of the vanishing point, you're off the road. 1 edge to the left, 1 edge to the right, you're on the road. It's not heuristics, it's not guesses, it's specifications. And anything that you can perceive, this is a general concept in ecological psychology, anything that you can perceive that is persistent, that does not change either over time or with a change in position, that has to have an invariant that underlies that perception. There has to be information that you are picking up that does not change, even though position changed, time changed. There has to be something underlying that. So, for example, physical size. Physical size has an invariant. And this is why when you walk towards somebody, it doesn't look like that person's getting bigger. It looks like that person stays exactly the same size, even though the pattern of their light, the structure of their light is getting bigger as they're getting closer to you. You don't perceive them as growing up or growing bigger. And the reason is because of an invariant known as the horizon ratio relation. And the horizon ratio relation, it's again, ecological psychology just puts the name right on the tin. It has to deal with the horizon. It has to do with the fact that it makes a ratio and that ratio is related. And basically what it says is that whenever you have an object, like a person, and you have a horizon, which we normally do in our environment, once again, important that we live in the world that we live in. Whenever you have a horizon and you have an object on the ground, that horizon is going to intersect that person at some point, or that object at some point on their body, right? So for example, here we see that the horizon intersects this individual right at their neck, just above their shoulder. And that intersection will not change regardless of where this person is in your environment. So as this person walks away, that horizon will still intersect their shoulder. And regardless of how far away they go, it will still intersect their shoulder. And more so than that, you can scale the environment based on where that hits, because the horizon is exactly at your eye height. The height of the horizon, and this is again just a mathematical thing we don't have to worry about, the height of your horizon is at your eye height. So this person is taller than everybody in this room, because at your eye height, your eyes would be right here if you were looking at this person. So they're at least half a head taller than you are. And you can scale the entire world in this way. And we'll end on this one because we're going to get into the trippier invariants next time. But I do just want to show you this in a real world context, because it is something that exists. But again, it's one of those things where I don't know if you've ever noticed it on your own, but once you see it, you'll never be able to unsee it. So here we have a scene of people walking. And one of the things that I do in my research is oftentimes I have to figure out the perspective structure of an image like this. And what I'll do is I'll start to look for things that are measured, that are mathematical, that are repeating. So if you take a look at the left side there and you take a look at those columns, you can see that there's this change in the color of the columns. probably when they ran out of one type of brick and they started using another type of brick, and that happened at the same moment. But what that does is it gives me a nice little line. And that line can be extended to a vanishing point. And then I can play the same game on the right side, and I can say, hey, take a look at these bricks over here. These bricks can also give me a line, and that line has a vanishing point. And where those two lines intersect, that's the horizon. Your horizon is right here. So we can't see the horizon, but we have enough information in this environment to figure out where the horizon is. That solves the issue of how can we judge people's heights when there's no horizon, because in any environment, you usually have enough information to figure out where the horizon is. So we have our horizon line right there. What I want you to do is, as this video repeats, take a look at the people that are walking. And other than the fact that they're bouncing up and down a little bit because they're walking, they stay at the same height for that horizon in this real world scenario. So that elderly gentleman that's close to us, it's hitting him right in the forehead. And it always hits him in the forehead. That tall guy walking away, it's hitting him about halfway up his neck. And it will stay there the whole time. That one elderly gentleman at the end, I'll call him out when he comes in there. He is right under the horizon. There he is. He's coming in from the left, right under the horizon, right under the horizon, right under, get out of the way. Right under the horizon, right? Right under the horizon. He's exactly eye height, that individual. And we can pick this up, and it's not inferred. It's not anything that we need to have make hypotheses about. It's not ambiguous information. It's information that's in the environment and specifies how big these individuals are, and importantly, does not change as they move further away or closer to us. And that could be the reason why we don't perceive them as changing size, because we perceive size as their horizon ratio relation. Okay, so we're going to get into the more trippy ones next time, such as perception of identity. So we'll do the thing that we've kind of typically been doing and kind of falling into this sort of challenge. So what I'd like you to do is kind of think about things that you perceive in this world that either don't change over space or don't change over time. So for example, we're going to get into identity next time. That is something that does not really change often over time. So if you have ever not seen somebody in years, right? Let's say that you had a friend in high school and you hadn't seen them in years, and then you encounter them on the street and you say to yourself, oh my gosh, Janice, I recognize you. What you're saying is that even though they aged, even though the perspective structure of their face changed, that invariant relation that specified Janice is still there. So think about other things that we perceive that do not change, either through time or through motion. And we'll take a look at some of those next time. And as we delve in deeper, like I said, into the trippy side of ecological psychology and invariance, and the trippiest side, which is affordances. So any questions before we wrap up? All right, that is it for today.